Great, let's get started. So it's a great pleasure to have Michael Levalls with us today. Michael did his PhD in Paris, working on some geophysics. He then did he did a postdoc under a Matthew Curie Fellowship in Cambridge, working with Gray Worcester, who's actually going to be here in a couple of weeks for the Steve Davis talk. And then after that, he returned back to France, and he is now at ESAM in Marseille, so Fluid Dynamics Institute. Michael has interests across many fields of physics, geophysics, fluid dynamics. He's been working on fluid dynamics problems across these different fields and also in some industrial problems as well. In addition, Michael has received many awards, in particular the LeConte Prize recently, which is given out by the French Academy of Sciences. And today, Michael is going to be telling us about fluid dynamics of Jupiter in the lab. So take it away.
Thank you. It's a pleasure to be here, and please, you're welcome to ask me any question you want. So I've tried to introduce things about Jupiter for people doing mostly fluid dynamics and things about fluid dynamics for people doing more observation, but you're welcome to ask any question if you want at any time. So Jupiter, you might all have seen that kind of picture. This is taken from the Hubble Space Telescope. So those are series of snapshots, okay? And you see that Jupiter, so its size is about 10 times the size of the Earth. And what you see are mostly bands and spots. So this is a great red spot. Okay, the great red spot here, it's about the diameter of the Earth, to give you a scale. So Jupiter is entirely covered by clouds, and you see those very nice structures. And all those structures are dynamic. So if I now switch to the next movie, so this is taken from Cassini, who came close to Jupiter. And they took one picture every day. So you see a movie of the flow that is going on. And you see that actually bands correspond to jets, eastward, westward, or westward, eastward going jets. And spots correspond to vortices. Okay. The typical velocities involved here are very large. So the bands are flowing at 100 meters per second, typically. And all those jets are very straight. Okay. So these structures with spots and bands, it has been observed for very, very long time. And actually the first observation date back to Cassini. So this comes from the 17th century. And the band and the spot were already there. So you have a huge planet, 10 times bigger than the Earth, very turbulent flow, but very straight, very well organized, and very long-lived. So that's what makes, from a fluid dynamic point of view, that's what makes Jupiter so special. The other thing that is very specific to Jupiter is that it is entirely covered by clouds. So all that we see here, if you do a vertical cross-section, actually, we are only seeing about 100 kilometers at the surface of the planet, and we don't see anything below it. And the planet, again, it's about 60,000 kilometers. So all that we see are clouds, and the different colors correspond to different type of clouds. Okay, but of course the question is to know how what we see on the clouds is corresponds to something that is happening below. And Jupiter is completely different to what you know on the Earth, for instance. So on the Earth, the clouds are in the atmosphere, and below that you have the ocean with a sharp interface between the two. Below that, you have the solid mantle, again, a sharp interface, and below that, the core, the core. In Jupiter, it's all done with the same principal ingredients, which is hydrogen. And you have hydrogen all the way from the top to the bottom, but it's changing its state because of the pressure. So in the atmosphere, you have gaseous hydrogen. Then because the pressure increases, it goes to a liquid at about a few thousand kilometers below. So a few hundred kilometers of gas, a few thousand kilometers of fluid. And then because the pressure keeps increasing, you end up with conducting fluid. So compared to Earth, it's like having a continuum between the atmosphere, the ocean, the mantle, and the core below it. And all that is fluid. There might be some solid part, but we don't know exactly if it's the case or not. So for a long time, people were saying there might be a solid core, but we are not even sure of that anymore. Okay, so in addition to observation from Earth or from Earth's orbit, there have been some space missions, including an orbiter, Galileo, in the late 90s. But today, it's a very exciting time for Jupiter dynamics because there is this JUNO mission, which is orbiting Jupiter for since 2016. And one specificity of the JUNO mission is the orbits they have chosen. So because it goes actually very close to Jupiter, it can go as close as a few thousand kilometers above the clouds. But there, it's a very dangerous environment. So then it goes away from it, so down to 8⁻⁶ kilometers to emit all this data, and then it goes back very close to Jupiter. But it's a very close view, a unique view, and it's going above the pole. So it's the first time that we do really see what is happening on the pole of Jupiter. So I'm just playing a movie now. So that's one orbit of Jupiter. You come from the North Pole, you go over the Great Red Spot here at about a few thousand kilometers, and then you go away. I can run it one more time with the lights off. Okay, so you see again all those spots, the bands, the Great Red Spot here. Now that's the Great Red Spot, and then away from it. And you see at the end of the movie, you have a very nice view of the South Pole, where you might see that bands are disappearing and you have more clusters of vortices at the pole. Okay, so JUNO, in addition to this very nice JUNO cam, has a lot of instruments on board. And what is especially interesting for my work is that it's also mapping the magnetic and gravity fields, which gives you insight into the deep, the depths of Jupiter. Because gravity and magnetic field, they come from the deep below the surface. So you can have information about what's happening there by looking at the data on the magnetic field and the gravity field. Okay, so what I try to do is to design lab models to try to explain those main features of Jupiter, and especially to try to understand how those flows that we see on the surface in the cloud layer, they organize in depth. So I'm just quoting this sentence from the paper after Cassini in 2005, but it's still the case. What is interesting here is that the fundamental physical process involved in the study of Jupiter attract workers from many disciplines, including physics, meteorology, engineering, and also planetology, deep geophysics, and so on. Jupiter atmosphere constitutes a human free dynamics experiment at a scale that could never be achieved in the lab, and one continues to challenge state-of-the-art computer. This is still the case, of course, and I want just to come back on those two last lines. Could never be achieved in a lab and challenge state-of-the-art computer. I would like to quantify this just to show you what we are really trying to do and why lab experiments are still interesting in addition to computational simulations. So in free dynamics, we don't talk about scale with a dimension. So we don't talk about the radius because, of course, in the lab, we will never do a 60,000 kilometer planet. What we talk about are balance between forces, and we introduce dimensionless numbers to quantify those balances. And here I will need in my talk 3 dimensionless numbers, which are written here. So the Aix-Marseille number, the Reynolds number, and the Rossby number. The Aix-Marseille number is a ratio between viscous effects and rotational effects. Okay? So it quantifies, when it's small, it means that you have strong rotational effects. The Reynolds number is a ratio between inertial term and viscosity. So when Reynolds number is large, it means that you are very turbulent and you don't care that much about viscosity and viscous dissipation. And the last one, the Rossby, which actually is a product of the two first numbers, is the ratio of inertia over rotational effect. So U here is the velocity, typical velocity, omega is the rotation rate. And so Rossby number larger than 1 means that you don't care about rotation. Rossby number below 1 means you do care a lot about rotation. And those are the numbers for Jupiter. So Eichmann is extremely small, which means that rotation is extremely important for the dynamics of Jupiter. Reynolds number is extremely large, meaning that the flow is very turbulent. And the Rossby number is smaller than 1, which means that inertia is dominated by Coriolis effect. So again, rotation does matter a lot, even if it's very turbulent. So it's turbulence constrained by rotation. Okay, so what can we do in the lab? So I'm doing tabletop experiment, maybe a little bigger than tabletop, but reasonable scale experiments. So it means that I have a typical size of 1 meter, a typical velocity of 10 centimeters per second, and I'm working on a rotating table, which rotates at about 1 rotation per second or 1.5 rotations per second. So it means that, and I'm using water. So viscosity is 10 to the minus 6 meters per second, omega is 10 radians per second, R is about 1 meter, and U is about 10 to the minus 1 meter. So you can compute all the numbers, and this is what you get. Eichmann is 10 to the minus 7, Reynolds is 10 to the 5, Rossby is 10 to the minus 2. Yeah?
Should there be another number with gravity involved?
We are doing iso density barotropic flow for now, but I agree it will come at the end of my talk. The next step would be also to look at the density profile of that. But for now, I'm just using iso-dense tree. Okay, so when you compare this series of numbers in experiments and this in Jupiter, you may have two reactions. Either you're pessimistic and you say, well, I'm 9 orders of magnitude wrong. So I cannot say anything. But if you do that, you never work in geophysical fluid dynamics or in astrophysical fluid dynamics because it will always be the case. If you are optimistic, you say, well, I may be wrong, but I'm in the good range, in the good limit. My Eichmann number is small, my Reynolds number is large, and my Rossby number is smaller than 1. So I have the good balance. Actually, I'm looking at the good dynamics. I'm strongly constrained by rotation and I'm fully turbulent. And I want to insist on that if I were doing numerical simulation, and by numerical simulation, I mean a direct numerical simulation, so solving the first principle equation of motion, so Navier-Stokes equation, with all the scales. The best I could do is an Eichmann number still 10 to 100 times larger, larger, and Reynolds 10 to the 100 times smaller. So in any case, with my experiments, even if I'm far away from the Jupiter, I'm still better than what we can do with direct numerical simulation. I insist on that. It is possible to use parameterized models, like you don't solve for the turbulence, but you parameterize it, or you use, since you are fastly rotating, you can use quasi-geostropic motion, so an asymptotic limit in the small Rossby number and things like that. But those are not solving the constitutive equations. They are solving models of the constitutive equation, so they need to be validated or not. And sometimes you might have surprises. So it's always good to come back to reality, to real flows, and to direct numerical simulation. And that's an important point for me because I have to defend that each time I submit a grant. So if you have questions, I'm happy and ready to discuss it. Okay, so the main point here is just that experiments, okay, we have problems, but it's still useful. The main pros is that we can reach more extreme regime in terms of rotation and in terms of turbulence. Then it's not always easy to set up an experiment, but once it's there, you can run it for a very long time. And you can make long-term measurements, which is always very difficult in numerical simulation. So you can explore the parameter range and have long-term statistics, which will turn out to be very important to study the dynamics of Jupiter and the long-standing jets and so on. Of course, there are cons also. The first one is that you cannot deal with the real geometry. For instance, you cannot do in the lab, or it's very difficult to have a spherical geometry with radial gravity. but we have way to handle this. I will show you after. Some physics are barely accessible, for example, effects of compressibility. So we're using water, so we are studying mostly incompressible flow. Magnetic field is also very difficult. And yes, so it's always, once you have your experiment, it's always difficult to make measurements. So you can have probe measurements, meaning that you measure the velocity or the temperature or something at one point using a small probe. You can also have non-intrusive measurements, like for instance, PIV, so particle image velocimetry, where you put particles in the fluid, you make a laser sheet, and you follow the tracking, you track the particle as a function of time, and that gives you access to the velocity. But that's only in a plane. So contrary to numerical simulation, you don't have access to all variables at the time you want. You still have to work hard to have data. But yeah, so the two, it means that what my point is that there is no best way to study the problems. The best way is to combine theory, numerical simulation, parameterized model, and experiments, of course. Okay, and that's what I try to support and to have in my grants. Okay, for this general introduction. So now let's start. So my talk will be in two parts. I will first look at the jets, and the big question here is to know how do you form those jets, how deep they are, and why are they so long-lived and so stable. So this work was initiated 5 years ago by with JUNO, who is at UCLA and was visiting in Marseille. So we built the first version of the experiment, but most of the work I will show you today is from my PhD student Daphne Lemasquerier, who is now a lecturer at Saint Andrew. Okay, so again, this nice picture of the jets. So those are very straight jets, and if you measure, track the cloud to have some idea of the velocity, 90% of the kinetic energy in the cloud is in this axisymmetric motion. So a large amount. So that's completely different to what we know on Earth. On Earth also, so this is from a MERA simulation, the Earth seen from the pole. You also have jets, but they are much more meandered. Okay. So you don't have 90% of energy in the axisymmetric motion. You have also lots of energy in the cluster. I don't know the exact number. I should have checked before, but you see from the picture that it's the case. So Jupiter is not like the Earth. And in the ocean, you also have jets like that. They appear when you do measurements, but only when you average them over a long duration of time. So this map here shows you the jets, so the velocity along parallel to the equator at a 1,000 meter depth, but those measurements are averaged over 2 years. So in the atmosphere, in the ocean, we also have jets, but they are much less straight and much less energetic. So what do we need as a minimum physical ingredients to make jets in the lab, to make a lab experiment that will reproduce the dynamics of Jupiter? We need 3 ingredients. The first one is to inject energy somehow, okay, in our system. And there also, the mechanism of energy injection is very different on Jupiter than it is on Earth for both the atmosphere and the ocean. On Earth, you have a large amount of energy that is ejecting from the sun, and you have a large difference between the pole and the equator. You have a large temperature difference between the pole and the equator. The amount of energy that comes from below, from the Earth itself, from the deep interior of the Earth, is smaller. On Jupiter, it's different. First, you don't have any significant difference between the pole and the equator, and then you don't have significant difference between what's coming from the sun and what's coming from the deep interior. That means that the injection is probably small scale. What is coming from deep is actually driving some small scale convection, and what is coming from the top is actually driving Morse convection, so thunderstorms and columns and things like that. So you're injecting energy at small scale and not at large scale, like on Earth, where you drive the large ALA cell from the pole to equator difference. But since you're injecting energy at small scale, and by small scale, I mean less than 100 meters. how do you end up with structures that are 10,000 kilometers in length? So to do that, you need an inverse cascade, which means that from the small scale injection, you need to build up large scale motion. So that's already something very surprising and unusual when you do fluid dynamics, because when you take a lecture in fluid dynamics, what you learn about is a Kolmogorov cascade of turbulence. So this is wave number, energy, forcing, so you inject energy at a given scale, and then from these scales, you go to smaller and smaller and smaller scales. So you have direct cascade of energy from the large scale you inject to the small scale where you dissipate. Okay, think about a drop of milk in your cafe. You mix, and then your drop is stirred and mixed and goes to smaller and smaller scale until it dissipates. We need exactly the opposite. And from a theoretical point of view, this does exist in 2D. So in 2D, there have been a theoretical study by Kolmogorov, and Eichmann, showing that because of the constraint due to the fact that your flow must remain 2D, you have an inverse cascade of energy, meaning that if you inject energy at some forcing scale, you will build up larger and larger and larger structures. And to show you that, this is just a movie solving for the Navier-Stokes equation in 2D. So you start from so this is the vorticity field. When you start from a vorticity field like that and you let it run with no dissipation, after some time you end up just with two big vortices. So you have just built up large structure from small scale energy injection. Okay, so inverse energy cascade works in 2D, but the world is, or Jupiter is 3D, of course. The good news is that this theory of inverse energy cascade still works in 3D, depending in some asymptotic limits. So the first one is that if you consider just a thin layer where vertical motion are limited compared to horizontal one, works like if it was quasi 2D. And the second possible limit is when you are in fast rotation. So when you are in fast rotation, all the motion along the axis of rotation are solidified. So to show you that, I just run here the class experiment. So this is just a record player. You have two tanks filled with water. This one is not rotating. This one is rotating at a constant rate. And I just do a small injection of fluid, isodensity. Just my injected fluid is dyed in red. So you see that without rotation, it will just spread and fill progressively the whole tank by very slow motion. In rotation, you just build a column. Because again, if your rotation is fast, you won't have any significant motion along the axis of rotation. So it's like quasi 2D. You are 3D because you are extending in the third direction, but you don't have significant motion along the axis of rotation. And there also the inverse cascade mechanism works. What does it mean for Jupiter? So it means that for Jupiter, you might think of two different models. And that's been a long fight between two communities over the year. On the left, you have the model from the atmospheric community. So people who are studying the dynamics of the atmosphere on Earth. So they are used to study the dynamic in a very thin layer. So they say, well, in Jupiter, we also have a very thin atmosphere. If we look at it, we will be quasi 2D. The second model comes from the deep geophysics community, people looking at core dynamics, which are used to have a very fast rotator. So they say, well, in Jupiter, everything is linked because, as I told you before, it's hydrogen going all the way up to down, going from gas state to liquid state, but all is connected. But since I'm fastly rotating, all my motion will be aligned with the axis of rotation. And again, I'm quasi 2D, so I have this inverse cascade mechanism. Okay, for the two models, I will come back to them after. Okay, so we have small scale energy injection inverse cascade with two possible models, depending on whether you consider only the atmosphere or the whole depth of Jupiter. And then if you keep having an inverse cascade, you will just end up having one big structure on the size of Jupiter. So at some point, you need some type of anisotropization. At some point, the fluid has to know that going north-south is not the same as going east-west. Okay, so that's a new, an additional parameter in my Navier-Stokes equation. It's called the beta effect. And there also you have two types of different beta effects. depending on which model you consider. So in the shallow model, what does matter, since you don't have motion in the, across the thin layer, you don't care about the whole rotation, you just care about the rotation along the local normal to the surface. So it means that at the pole, you feel the whole rotation. At the equator, it's almost like you were not rotating at all, because you are in thin layer, the rotation is like that, so you don't feel it across the thin layer. So you have a change of the influence of the rotation parameter from the equator towards the pole. That's the beta effect. So beta effect is just the projection of the amplitude of the rotation vector along the local normal to the surface. Here, the beta effect comes from the fact that the depth of the water column, of the fluid column, changes as a function of radius. When you come from the pole and you go towards the equator, you first increase and then decrease the depth of your fluid. And that also has an effect, which is known as the ice skating effect. So you know that when you have an ice skater that is turning, when she or he has her arm spread, she rotates slowly, and when she brings her arm together, she rotates much more rapidly. This is conservation of angular momentum. So here in my planet, it's the same. If I have a thin layer, vertical layer, and I put it away from the equator, I stretch it, so I start beginning rotating faster. So this is the beta effect, which is related to the radial dependence of the depth of the water column, of the fluid column. And this is also a beta effect. Why is it called beta? Because when you write down the equation, it appears like this, and the two mechanism appears with the same parameter here. So it's beta times the radial velocity. So I won't go through the equation. All that I need from my talk is that, so you have a new parameter beta that characterizes the fact that rotation is not uniform, and that characterizes the fact that going east, west, or north, south is not the same. When you take a vertical structure and you move it eastward, westward, you don't feel the beta effect, but when you're moving north or south, you feel the beta effect. This beta parameter has a scale of 1/m², which means that I can build up two new length scales in my system that will be representative. So I introduce them here. The first one, epsilon here, is the energy, the flux of energy in my turbulent cascade. So from equilibrating the beta effect with the flux of energy, I can build up a new number, a new length scale, which is called the transitional scale. So I have an inverse cascade, and when I reach this number, it means that my inverse energy flux begins to feel the beta effect. So above this scale, for structures larger than this, going east, west, or north, south will not be the same anymore. So transitional scale, and the other one is the Rhine scale. So the Rhine scale is the scale at which the large scale at which the system will equilibrate. So it's you can build up by the velocity divided by the beta effect. So it's where nonlinearity compensates the beta effect. So that will be the size of the larger structures you will see. So it was derived by Rhines. So it's typically the size of the jets. Okay for that. So I know from the theoretical point of view, to make a model of Jupiter, I need small scale energy injection, inverse energy cascade, and some kind of beta effect of anisotropization. So now, how do I do that in the lab? So first thing, as I already told you, I cannot have a spherical geometry with radial gravity. So I will work in a cylindrical geometry. So that's a big change, I agree. It's not my big cylinder here, so it's a cross section of the cylinder on my rotating table. It doesn't look like a planet, but you will see that the physics is the same. One important point is that if you look at my cylinder from the pole, or if you look at Jupiter from the South Pole, for instance, it looks much more closer. Okay? And in particular, I have this beta effect going from here to here, because once I set my cylinder into rotation, I will come back to this after, the free surface becomes parabolic. So the depth of my fluid layer increases when I go away from the pole, which is my axis of rotation. Okay? So I have an inverse energy cascade because I rotate fast. I have an anisotropization because the depth of my water column is changing with radius. And finally, I need some type of energy injection. So for that, I just use a Jacuzzi. So I have a small plate at the bottom with lots of holes and injection and suction of fluid from that hole and a pump. And then I run everything and I inject energy at a small scale given by the distance between one injection and one suction rotation. So this experiment is called the Jovian jet jacuzzi. And this is how it looks like. So that's the first version of it. So that was 5 years ago with JUNO when he came and visited. We had no money at all, or almost no money. So, but we have good ideas. So we bought a trash bin, $100. We bought a GoPro, $300, and then we bought a pump for flooding in your garage when you have the water. So also $100 in at Petco or something like that. Okay. So the GoPro is over there.
Oh.
So important point, you're right. We need to make measurements in the rotating frame of reference because we look at slow motion within the rotation of the pen. So we need to make measurements from the rotating frame of reference. And that's why we choose GoPro because it's easily remotely controlled. So it was a cheap experiment. I'm kidding, it's not that cheap because we still need the rotating platform, which costs a lot, but we already had it from before. So, but the setup itself, okay. And to make the jacuzzi, so we took a plate of acrylic and drill holes. The important point, and then make some tubing after that. The important point, so blue is injection, yellow is suction, and you see we don't have any axisymmetric forcing. It's really random in the azimuthal direction. So we will not force directly the jets here. We make a random pattern. And to make measurements, so we make two types of measurements. The first one is we inject some dye at the surface of the fluid and we follow it with a GoPro. So all these are differential. You are on the rotating platform, rotating at 1.5 rotation per second. And then you follow the formation of the jet by following the dye. And the second type of measurement, so we have tiny particles floating at the surface and we can follow them through time. Okay, so this is 1 meter in diameter. This is about 15 centimeters. And over there, it's 1.2 meters. It's huge, and it's a key thing to get the good dynamics for Jupiter. I will come back to that after. Okay, so then I got some money. So I redo everything, but better and nicer. So instead of having, before I had 64 injections, we made even more to get a smaller scale of energy injection and to have a large range of inverse energy cascade. But still, again, no axisymmetry in the injection pattern. We also made that was kind of tricky. So the bottom layer plate, instead of being flat, we shape it with this very specific shape here. So why is that? It's because one ingredient is this beta parameter, and beta parameter is written over there is 1 over h dh over ds. So it's 1 over the water depth divided times the radial derivative of the water depth. So to get a constant beta, because all the theory are developed with a constant beta, you need to compensate the free surface, which is always parabolic, because it's just an isobar, by the specific shape at the bottom. Okay, so that costs a lot, and the most difficult part was to find a company capable of shaping this 1 meter in diameter plate. And then, very important also to make better measurements. So we install a full PID system in the rotating frame of reference. So you see we have a very nice camera on the top over there. We have a laser sheet here, which make a cross section just above the bottom. All motion are aligned with the axis of rotation, or mostly aligned with the axis of rotation. So one cross section is enough. And we have the computer recording the images also in rotation. Okay. So that costs a lot. So when you rotate it at 1.5 rotation per second, you want everything to be fixed. So we use a lot less tape and much more regular taping for this experiment. Okay, so this is where when it runs. Can I have the sound? So one more time. This is real-time moving. Okay. Okay, so with this set, once we have this setup, it's nice because, as I told you in the introduction, we can run it for a long time. We can make nice measurements, make statistics, and so on. So this is an example of the velocity field, azimuthal velocity field that we measure in the rotating frame of reference. So we first wait for solid body rotation, everything is settled, and then we turn on the pump, and this is what happened. So we first see the small jet, but rapidly they organize as jets. But this first regime is not the one we are looking for, because actually when we analyze it, we have one. Oh, here is my injection pattern. I have no axisymmetric injection pattern, but I have 6 rings of injection. Each is controlled by an independent pump. And along one ring, I go from one injection section, injection section. And it turned out that this specific regime is not very interesting because we have one retrograde jet above each ring of injection. And of course, in Jupiter, you don't have fixed injection point. Everything is moving around. But if we wait a little more, this first regime goes into a second one, where you have much stronger jets, and those jets are independent of the injection pattern. So this is the regime we are interested in. This is the regime of Jupiter, the zonostrophic turbulence regime.
How long does that take to double the time?
So it's an instability. So we have an exponential growth depending on how far you are from threshold. Here, the movie in real time is it's accelerated 40 times, 10 minutes. So in this movie, it was a few minutes to reach a steady state. And one very interesting point is that once you reach this steady state, it stays there. But you do not always get the same pattern. You always get the same characteristic, but if I run twice the same experiments, one time I might have a retrograde jet here, and the next time I might have a prograde one. So you have multiple stability, multiple possible stabilities, but once it's there, it is very, very, very stable. So I will show you that after. So again, the two regimes. The first one where you see with the dot lines that each retrograde, each red jet is above, so that's just mixing above the injection pattern. But this one, nothing, not related to the injection. And we did some additional numerical simulation to further test that. We could not make several injection patterns in the lab because each time we need to remodel this bottom plate, which costs a lot. So we had complementary numerical simulation to look at that, one of those parameterized models to check. And this is a space-time diagram. So here you have the time in rotational units. And this is a radius in my tank. So you see that this is the first regime. So you have just a jet above each injection pattern and nothing more. This is the interesting regime where you started with one jet above each ring, but then they merge, they organize, and once they are there, they stay. Daphne, the PhD student, runs the experiment during 10 hours, and during 10 hours we could do nothing but they stay here forever, even if it's very turbulent. Again, the Reynolds number is 10 to the 4. Okay, so we were very happy. This is the first realization of this zonostrophic regime, which is relevant for planet. And why? So there were experiments before. So, but this is an example in a very large rotating table in Grenoble, in France, so 13 meter in diameter rotating table, but not rotating very fast. And this is one example, one picture of what they get. So you see, it looks closer to what we have in the atmosphere, I mean, with the meandering jets. This one is another experiment with a smaller setup. some small scale injection also, but also rotating much slowly, so with a smaller beta effect. And they get, those are the measurements, instantaneous measurements, and they get jets, but only on average, when they time average the process, like in the ocean. In our case, if we take a picture, we have the jets, so we have instantaneously lots of energy in the jets. So why is that? So I introduced, in introduction, I mentioned those three numbers. And actually, I told you the Rossby is the product of the two, so there are two independent numbers. So this is an Ekman, so viscosity over Coriolis, Reynolds, so non-linearity over viscosity. Those are the experiments, us, the Earth, ocean, atmosphere, and Jupiter and Saturn. So you remember 9 orders of magnitude away. So we do a little better than previous experiments, but not that much. And we are not any closer to Jupiter. And this is because we are missing one parameter. And this parameter is related to this beta effect. You remember the beta effect that quantifies the anisotropy. So from this beta effect, we can define two length scales. The length scale when the inverse cascade begins to fill the beta effect, and the large scale saturation. So we can define a dimensionless number, which is a ratio between those two. And if we draw the regime diagram in this new space regime, so this is Reynolds number, and this is this ratio. Well, previous lab experiments, Earth, ocean, and atmosphere, they are low R beta number, while we are above, and Jupiter and Saturn are above also. Okay, so we did better because we have a strong R beta, and we have a strong R beta because we have a strong beta, and because we are deep rotating fast, and we have this huge difference between the center and the side. So one reviewer of the paper said that our work was not so interesting because all that we did is to rotate faster, and that's it. But I hope there is a little more than that in our work. Okay, so this transition between Earth-like jets and giant gas jets, they were predicted, but in 2D models of turbulence and in 2D simulations before. So it's the first time that we actually see them in a real 3D lab experiment. And yeah, we are pretty much in agreement with the 2D simulation here. They predicted a threshold at about 2.5, which is about what we can see in our study. So can we do something more about this? We can also analyze the spectra. So people have looked at the Cassini data, so pattern of clouds and how they move between two successive pictures. And they have defined spectra. So this is the wave number, the kinetic energy, and they separate the spectra in two components. The one for the axisymmetric motion and the one for the perturbation once you remove the jets. Okay, and they compare that with theoretical work from 2D. So in the zonal jet kinetic energy spectra, they predict a slope -5. And in the residual kinetic energy, a slope -5/3. So that was well reproduced by a numerical simulation using shallow models or 2D models or shallow models, but not from numerical simulation having 3D models. And during a given amount of time, people say, well, Jupiter jets are shallow because numerical simulation of deep jets are not capable of reproducing those spectra. Okay? So if we do that with the lab data, so this is not the best slide, I'm sorry, but we drive you through them. So in purple, it's the zonal kinetic energy with a theory that predicts -5 slope. So you see our data here, and the -5 slope works okay. And the blue spectra is a residual kinetic energy with a prediction of -5/3. And you see that at least between the forcing injection and this transitional scale, we also recover part of this spectrum. So it is not correct to say that the jets in Jupiter are shallow because they are only the only one reproducing the spectrum. Also, the deep models reproduce it. Okay, so what's the end of the story? So JUNO is going around Jupiter, and we have some data. And in particular, we have gravity data, so measurements of the gravity field. So cascade, here, use this gravity field, and more specifically the asymmetry between the north and the south component of the gravitational field, to inverse it and correlate it with the depth of the jets. And he said that, so I'm quoting what he writes in his paper, Jupiter bands extend down to depths of thousands of kilometers beneath the cloud level, much deeper than what we generally thought of as Jupiter weather layer in a few tens of kilometers. So everything seems to come all together here. We have a lab model showing that 3D zonostropic turbulence matches with theoretical prediction. The data are showing also that it seems to be the case in real Jupiter. And now what we could hope to do is to use those predictions to access to parameters like the flux of energy and the beta parameters that are unknown for Jupiter. So now that we have the model that is working, we can use the data to give access to things we cannot measure in the planet and better understand the injection energy process, the dissipation processes in Jupiter. Okay. So, as I told Daniel, I have several ways to go out of this talk, and I'm already running out of time, so I'm going directly here. So we were focusing on the latitudinal jets. So now the question is, what happened in the pole? Because again, one big surprise from JUNO, it was the first time something went and see the pole, and there the jets disappear, and we end up with clusters of cyclones. So those are two pictures, one of the North Pole, one of the South Pole, taken with infrared camera. And you see that here, it's easier to see. You have 1, 2, 3, 4, 5, 6, 8 huge cyclones clustered around the central one. And they saw that for the first time during the first flyby in JUNO in 2016. And they are very stable because they keep seeing it each time they come back. So after 5 years, those structures is always stable. Okay? They rotate like that and they spiral like that. So I think the whole cluster is rotating with the vortices.
They are actually, there's shear between that.
They rotate like this,
yeah,
and they rotate like this around the pole. Everything is rotating and rotating. And so those, one big surprise also is that those are cyclones. While on the side of Jupiter, and the great red spot, for instance, is an anticyclone. And I think 90% of the vortices that we saw before going at the pole were anticyclones. And here on both poles, those are cyclones. So that's also kind of a surprise. And so their radius is about a few thousand kilometers. We don't know how deep they are, but a priori, they might be shallow structures. So they might be limited to the atmospheric size, because otherwise, if they were going deep, they will also dissipate at the magnitude boundary. But that's not for sure at all. At least that's a hypothesis we took. Okay, so those are shallow structures floating, and you have turbulence below it that gives rise to jets on the side. So very rapidly, what can we do with our lab experiments? So it's a starting work. So I just took preliminary results. So we have our tank here, and we remove the plate, the specific shaped plate, so that we have a flat bottom now, and we add a stratified layer at the top. To do that, we just have salty layer here and fresh water here. Sorry. And then to make the cyclones, we have pipes here that come and make some suction. And if you make a strong suction in rotation, you will generate cyclones. We can make either one or up to 8 and one central, depending on the terms we turn on and off. Okay, and so why is it close to Jupiter? It's because you remember this beta effect that we try to have constant on the side of Jupiter. At the pole, it's different, because at the pole, in a thin layer, you see that the local normal goes from here to here. So the beta effect at the pole is 0. And that's exactly, so what I'm saying is that just that my parabolic free surface without bottom compensation At first order, it's like the spherical shape of the pole. Okay, so we have done some lab experiments and some numerical simulation with just one cyclone to begin with. And what we see is that the cyclones, if you generate it away from the pole, it goes towards the pole. It goes towards it. So all cyclones have a tendency to accumulate, to agglomerate at the pole. Then at the same time, the vortices are shielded, meaning that they have like a circle around them that prevents them from merging. So the clustering at the pole of Jupiter is probably coming from a balance between the fact that they want to go towards the center because of the beta effect, and they don't want to merge because of their shielding. So it's a very subtle balance, and I just show you here three different movies. So those are the same vortices, same order vortices, 6 of them. This is for a strong beta effect, strong slope going to 0 at the pole, small and intermediate. And what we see is that in the two extreme case, we just have vortex merging, and at a given small parameter space, we might have stable cycles. Yeah, so I'm just trying now to do that in the lab, and this is just the first picture we get from the lab. So this is the top view of the streamlines of the jet, and you might see. So we started with 8 different cyclones, and we end up with clusters here that can persist for a few rotation time, but we have not yet obtained neither the 8 cyclone pattern from the North Pole nor the 5 one, but we are going towards it. And I stop there. I thank you. And I take any questions.
Thanks very much, Michael. I can attest that when you're in a room with that tank going at more than 1 rotation per second, and the water level changes over a meter, it's a bit scary. So it's pretty impressive.
There is a grid in front of the student to protect it.
Yeah, some more questions.
It's very difficult to do 2D actually in the lab. Sorry? It's quasi-2D, but it's really 3D. You have some vertical motion anyway, just that they are smaller in amplitude than the horizontal one. So the only experiments I know about which are doing 2D fluid dynamics are experiments on a soap bubble. So the soap is very thin, and there you can have really 2D fluid dynamics. So some people are looking at those type of problems on a soap bubble, and they make vortices and they follow their evolution. So the transition, the depth of the jet, from JUNO mission, we know it's at least 3,000 kilometers, but we don't know exactly how it is. And it might be related to the second transition for the hydrogen. It's where it becomes conductive. So the limit of the depth of the jet might come from the fact that you have some magnetic damping at the bottom, and that limits the penetration below, because below it would be fully MHD dynamic. No. And in the lab, I don't know how to do real 2D.
What's the main state you're showing at the end with any the cyclones on the poles, cyclone?
So I think one answer is that if you write down the equation, the cyclones are moving towards the pole, the anticyclones are moving away from the pole. So that might be why you end up with this cluster of cyclones at the pole, and mostly anticyclones on the side, like the great red spot and all this. And then the big question is to know how could this pattern be so stable? Imagine on the Earth, it would mean like having 5 huge storm clusters and staying there for 5 years at the same place without moving. So it's something that we cannot understand. And again, it's even bigger than here. Each cyclone, its storm is 2,000 kilometers. And you cluster them, it's fully turbulent, you have injection of energy or the pattern everywhere, and it stays there. That's a big surprise of this dynamic. Thank you.
So again, in this last set of experiments, you said you are getting some structure, but they're not very stable, and you're working on it. What do you think? Are you gonna try and change the experimental configuration so that you can get maybe the right data quantity, or is there more that you think you're gonna have to?
There is more than this. We have spent a great amount of time just to have one stable cyclone. So I come back, I had a question about the density before. And for this specific experiment, if we try to do it with one layer, that was our first try, so they are deep like the jets. And so the cyclones go all the way down to the bottom and they dissipate because they lots of viscous friction. So the first thing we discovered that there must, in our experiments, they must be shallow, maybe in Jupiter also. In my experiments, they must be shallow so that they do not bend at the bottom. And then we try to change the density jump at the interface here, and it must not be too strong. If it is too strong, we don't have stable jet, stable cycle. So there is already something to understand here. So what is the density profile you need to have stable vortices? And once you have stable, then you make stable. You must find the good balance for them not to merge. Once you have a cyclone that is stable, it will go towards the center, but you want it to go not too fast towards the center, so otherwise they merge. And you don't want them not to be shielded enough, so otherwise they merge also. So it's a subtle balance. In the lab, it seems very difficult to do, except that in Jupiter, that's the thing you see. So there must be some solution there.
Just following up on that real quick, is this rotated at the same rate as the Jets experiment?
It's rotating a little slowly because you see the interface.
Okay, that's what I thought.
Yeah. So it's half the rotation rate. It's half rotation. It's 1/3 of the rotation rate of the jet experiment. Otherwise, it's very difficult not to mix this stratified layer. So we start with it's easy to done at rest. So we have salty water, 5 centimeters of fresh water flowing above it, and then we rotate very slowly. Otherwise, during cleanup, we just mix everything and we cannot do the experiment. But we are trying to go faster and faster to see if it's also one of the important parameters for their stability. So this was done at 30 rotation per minute.
One quick question. A very nice talk. I was curious about one of the more technical aspects of the experiment. I was thinking about this rotating platform and wondering how critical is it that you eliminate vibration? How critical for the experiment?
Okay.
With a very smooth rotation.
Yeah. So that was also, so when you do code, you have to spend lots of time developing your code, but when you do experiments, you need to find a good place to buy things. So this rotating table is air bearing. And we bought it from the industry where they have, they need to cast big cars or things like that. So they are very nice air bearing platform, which rotate very smoothly, very precisely. And also you don't care about the leverage of weight, which is also very important. I think our table is very specific compared to other tables from other groups where they are not air bearing, so they go through a bearing which is that size. In that case, you can take much less weight and you have to equilibrate everything. So if you put a laser on one side, you have to put the same mass on the other side, otherwise you do that. With our platform, so we can have 1,000 kilograms in rotation at 1.5 rotation per second. And you don't see any vibration, you don't see any problem of vibration. And the last point is that it's much cheaper than the ones they built specifically for the lab, because it's industrial stuff, so they produce it in series. The only developing part was to control the velocity, because in the industry it's controlled to have precise angular displacement, and we want continuous rotation at a given rate. So that was the only development we need to do compared to the industrial. I can give you the advertise.
Okay, I think we're running out of time, so if people have other questions, please come up and ask Mikhail, and otherwise, let's thank
Thank you.
again for that great talk.